Hello. Our paper is titled Unlinkable, Updatable Hiding Databases and Privacy-Preserving Loyalty Programs. The authors of this paper were myself and Alfredo Rial, and this work was done while we were both at the University of Luxembourg. This paper has also been funded by the Luxembourg National Research Fund. A loyalty program is a marketing strategy where you have a buyer who makes some purchases from a vendor. And then this vendor collects information on these purchases, collates them, and eventually computes profiles for every buyer that purchases things from this vendor. And this is done typically in exchange for loyalty points, but this can reveal privacy-sensitive information. There are two main types of existing schemes in literature. The first type relates to schemes where vendors are not allowed to collect purchase histories at all. The second type relates to cases where vendors are allowed to collect some information on purchase histories. So in the first case, you have schemes that use blind signatures, updatable anonymous credentials, and unlinkable loyalty cards. And then you also have blind signatures and anonymous credentials in the second class. Now, when it comes to these existing schemes, there are a few shortcomings. The first is that all purchases are not unlinkable. The second shortcoming is that there is a lack of privacy with regard to purchase histories, as in they reveal too much information. And finally, these schemes lack modular design. We propose a scheme which resolves these shortcomings. Firstly, we ensure that all purchases made in our scheme are unlinkable. And then the scheme preserves buyer privacy and avoids purchase history disclosure while still allowing for profiling. And finally, we have designed our protocol modularly using the UC framework. So in this paper, we have come up with a new definition for an ideal functionality for what we refer to as a hiding database. And then we have a functionality for our loyalty program. And finally, we have a UC secure loyalty program scheme. We use the universal composability framework to design our protocols. And the basic idea behind the universal composability framework is that we have an ideal protocol which consists of the parties in the protocol themselves and an ideal functionality. The ideal functionality gathers all inputs from these parties, computes the outputs, and sends them back to the parties. And this functionality is also designed in such a way that the security properties we wish to guarantee with the protocol hold. So in a sense, this protocol is secure by definition. And now we say that a protocol securely realizes this ideal protocol if we have an entity which we refer to as an environment, which can interact with the ideal protocol and a simulator. And on the other side, it interacts with the protocol in the real world and an adversary. So if the view of the environment in both cases is the same and it cannot distinguish between the real world and the ideal world, we say that the protocol securely realizes this ideal protocol and the security properties hold. And we use this framework to define the protocols in the following slides. So we basically we come up with an ideal functionality for what we want to do with the properties that we wish to guarantee. And then we have a construction for this, the real protocol, which securely realizes the functionalities that we've defined. So this is the ideal functionality for our hiding database, and the database supports two operations. The first is a read operation, where a reader can read an entry in a database whilst proving to the updater that it is reading a valid entry. And this, during a read operation, both the position and the value of the data being read are hidden from the updater. In an update operation, an updater can update a reader's copy of its database without reading the contents of this database. And multiple readers can interact with this ideal functionality, but we have just one updater. There are three security properties we wish to guarantee with this ideal functionality. The first is that of unlinkability. The functionality uses a unique pseudonym to hide the reader's identity from an updater. And then we also guarantee hiding in the sense that the functionality reveals only commitments to the updater upon a read interface invocation. And these are hiding commitments, so the updater does not get to learn the contents of the reader's database. And finally, we also guarantee unforgeability, so that the reader cannot modify the database itself and it cannot read false database entries. The reader can also not make the updater update an older version of the database. We now propose a protocol in the Universal Composability framework that securely realizes the ideal functionality for hiding database that we've just seen. We will also describe how this construction allows for read and update operations. We use a vector commitment scheme to store databases in our protocol. A vector commitment scheme allows you to commit to a vector of values, and this vector commitment can then be opened to any position and value in the vector. And as every value in this vector is associated with a position value, we can use this vector to store a database of the form I_VRI, where I represents positions and VRI represents values in the vector. The vector commitment scheme we use in our protocol guarantees two security properties. The first property is hiding, wherein the vector commitment does not reveal any information on the contents of the vector itself. And the second property is binding, which basically means that you can't have a vector commitment that commits to two different vectors. Another property we guarantee with our vector commitment is that of additive homomorphism. So let's assume that we have two vectors x1 and x2, and we generate vector commitments to these vectors, so that's vc1 and vc2. With a homomorphic operation, we get another vector commitment, and this third commitment is a commitment to the vector we receive as the result of combining x1 and x2. We will now look at how we allow for read operations in our hiding database. When a reader first interacts with the updater signs a vector commitment to an initial database DB and sends both the database and this vector commitment to the reader. The reader then re-randomizes this vector commitment VC to VC dash and proves to the updater in zero knowledge that VC dash is indeed a re-randomized version of a commitment that was previously signed by the updater. The reader can now prove statements about the database committed to in VC dash to the updater. And that brings us to the update phase of the hiding database, where the updater updates a reader's copy of its database with some information while the reader's data is hidden from the updater. So what you see on the first line is the set of entries that the updater wishes to update the reader's copy of its database with. And the database on the second line is the reader's copy of its database, which is hidden from the updater. The updater computes a vector commitment VC2 to its database of updates, and the reader already has a re-randomized version of a vector commitment from the updater. So through homomorphism, we have a homomorphic operation which gives us another vector commitment VCU, which essentially is a vector commitment to the database which we get as the result of combining these values. And this new vector commitment is sent to the reader. The reader does the same the reader takes these updates and updates its own copy of its database, and it updates its local copy of its vector commitment with this new vector commitment VCU. We also make use of a double spending detection mechanism in our database, where the reader and the updater compute two random values S1 and S2 respectively, and the reader generates a commitment C1 to S1 and sends this commitment to U during a read operation. U in turn generates a commitment C2 to S2 and computes C, which is the result of an operation, a homomorphic operation between C1 and C2, and signs this commitment along with every vector commitment that is sent to the other party during an update operation. The commitment and S2 are both sent to the reader. And now when the reader invokes the read interface again, it re-randomizes C and sends it to the updater, and then proves to the updater that this was a C that was first signed by the updater. And later on, the reader opens the C dash to S, which is S1 plus S2. And now the updater checks if S has been received before. And if this is not the case, then U knows that the reader is not reading an older version of the database. And because we're doing this, these steps have to be repeated for every read and update sequence. and the message space of the commitment scheme we're using should be large to avoid collisions. In a read operation, the reader must compute openings for every position that is read, and because we're doing this, computation costs grow linearly with the number of entries in the database. However, we can store these openings and update them with cost independent of n. The reader also computes a commitment C1 with constant cost. And in the first update operation, computation costs grow linearly with n, but are constant if the first database is a vector of zeros. Subsequent updates involve the homomorphic property of the VC scheme. So then these computation costs grow with the number of positions that are being updated, but they're still independent of n. And to summarize, the amortized computation costs are independent of database size, which makes our instantiation practical for large databases. And now we come to the ideal functionality for our loyalty program, where we have 5 interfaces. We use a unique pseudonym P for every operation except an update DB operation between a buyer, a vendor, and the ideal functionality for this loyalty program. We do this to allow for unlinkability. First, we have a register interface where the buyer can register with a vendor for a loyalty program using a pseudonym. And then we have an update DB interface where the vendor can update a buyer's copy of its database. We also have a purchase interface where a buyer can make purchases with the vendor. And we have a redeem interface where the buyer can redeem some of its loyalty points with the vendor. And finally, we have a profile interface where the buyer takes a function as input and reveals the output of this function to the vendor. We propose a protocol in the universal composability framework that securely realizes the ideal functionality for a loyalty program that we've just seen. And we're also now going to describe how this construction has been designed modularly and how it allows for unlinkable purchases and how it also preserves buyer privacy while allowing for profiling. Now, because we've designed our protocol in the UC framework following modular design, we make use of multiple ideal functionalities in this protocol. The first is that of a hiding database, and then we have one for non-interactive commitments, another for a pseudonymous channel, and 2 for zero knowledge. Because we're using multiple ideal functionalities, we need to ensure that 2 or more of these functionalities receive the same input in several instances in our protocol. So for instance, we need to prove that we are reading the same loyalty point value from the reader's database, whilst we're proving this to the updater by sending it to an ideal functionality for zero knowledge. In such cases, for instance, the buyer takes this value and sends it to the non-interactive commitment functionality and receives a commitment and its opening as output. The buyer can then send this commitment along with the value itself to every functionality, and these commitments are sent to the vendor from these functionalities as output. The vendor then checks whether these commitments are the same, and because the binding property holds, we ensure that the initial values were the same. And here we describe how we allow for the registration phase to take place in our protocol. The buyer invokes the read interface of the hiding database for the first time, and the hiding database then sends a response to the vendor. The vendor then invokes the update interface of the hiding database with an empty database as input, and this in turn initializes a database which is sent to the buyer. The best way to understand the purchase phase would be to imagine a card payment made with a scanner. So when you tap your card against the scanner, it authenticates with the scanner, and the vendor already knows the price of the item you're trying to purchase. So this amount has been keyed into the scanner, and the scanner just updates this card. So in a similar fashion, the buyer invokes the read interface of the hiding database, and the vendor receives another message from the hiding database. Now the vendor invokes the update interface with a database of updates, which represents the updates to the purchase history of the buyer for this purchase and the updates to the loyalty points stored in this database. At some point, the buyer may wish to spend its loyalty points. To do this, it invokes the read interface of the hiding database to read the last entry in the database. This is where the loyalty points of the buyer are stored. The buyer then uses the zero knowledge functionality to prove that the amount of points it wishes to spend lies in the range 0 to the amount of points that it already has. And we use the method we spoke of earlier to ensure that the same loyalty point value is sent both to the hiding database and to this zero knowledge functionality. The vendor now uses the update interface of the hiding database to update the loyalty points stored in the buyer's database. So we just deduct the points that have been spent, and this updates the database of the buyer. In the profiling phase, the buyer receives a function as input. So for instance, this could be an average function that computes the average of all purchases made by the buyer without revealing the purchases themselves. And the buyer uses the read interface of the hiding database to read a subset of entries that are required to compute the result of function f. The buyer also uses a zero knowledge functionality to prove the correctness of the evaluation of this function and to prove that it has read the right entries from the database. And again, we use a non-interactive commitment functionality to prove that the same values are sent to both the hiding database and the zero knowledge functionality. We implemented our protocol and then measured the execution times of all the phases in this protocol. We also varied the size of the database we used between 15,000 entries to 65,000 entries. As you can see from the table, the execution times are largely independent of the database size. And when it comes to profiling times depend on the number of entries we use for the profiling function. To conclude, our protocol provides additional functionalities whilst also maintaining communication and computation costs that are similar to protocols that do not provide them. The purchases in our protocol are always unlinkable, and the scheme preserves buyer privacy and avoids purchase history disclosure while still allowing for profiling. And as we've used the UC framework to design this protocol, it follows modular design. Thank you.